Hi, welcome to this lesson on number patterns, infinite geometric series. Here we're going to be looking at deriving the formula of an infinite geometric series. Okay, so an infinite geometric series has this following form. We denote it by S infinity, S sub infinity. As we know, S sub n for the geometric series had one of two formulae depending on the value of r. It was either a times r to the n minus 1 over r minus 1, and we use that when r is greater than 1, and we just switched it around and said 1 minus r to the n over 1 minus r if r is less than 1. This was for the finite case. But what happens in the infinite case? You're adding up the first term, plus the second term, plus the third term, plus the fourth term, plus the fifth term, and you don't stop adding. You just keep adding all those terms. How do we know this sum exists? That was the question that Zeno posed in ancient Greece. Because if you imagine we added the following series infinitely, 1 plus 2 plus 3 plus 4 plus 5 onwards, that does diverge to positive infinity. And we say that the sum does not exist as it diverges off to positive infinity. But we are interested in finding infinite series that tend towards a finite value. So we can actually impose a restriction on our geometric series formula to get an exact value for the sum of an infinite number of terms in a geometric sequence. So for a finite geometric series, we derive the following formula. So I'm just going to use the second formula. Both these formulae are equivalent to each other. We just decided to rewrite one as the other just so that the denominator had a positive term. But both of those are the exact same formulae, just that a negative sign was pulled out of the one. So I'm going to use this one, and we're going to see why we're actually going to use this one. All right. So what happens when we add infinitely many terms? And so basically as n goes towards infinity. The numerator term of the sum is this guy here. A times 1 minus r to the n. So if n goes to infinity, then this term r to the n, this r to the n term, will either diverge to positive or negative infinity, or it will oscillate and not converge to any number. Okay, so how do we get it to converge to a finite number? So I'm going to show you in the next slide what happens depending on these r values. Why does it diverge to positive or negative infinity, and why does it oscillate and not converge? So the condition that we're going to impose on the constant ratio r is in a certain interval, and it's this one here. So this is the holy grail, the crux, the most important property that your constant ratio r must satisfy in order for a infinite geometric series to actually converge. Because what will happen is that the numerator term, a times 1 minus r to the n, and you can see I'm only focusing on the numerator term because that's the only term that has n. In the denominator, it's just 1 minus r. That's going to be a finite number. It's that r to the n term that is the issue. And we need to determine, well, what values of r, when we look at r to the n, what will happen? Will it diverge to positive or negative infinity? Will it oscillate and not converge? Might it oscillate and converge? That's what we're going to see now. So let's have a look at an interpretation here. So we say that this is the holy grail here, when r is between -1 and +1, not including those endpoints. So I have the strictly less than signs there. So let's have a look at the first part of this here. So -1 less than r and less than 1. So I'm looking at this first portion here. That's when r is less than 1 but greater than 0. So why do I do that? It's because on my exponential graph, I know how to plot this. So for example, let's take r equals a half, for example. So you have a half to the power n. If you plot that, this becomes an exponential graph and it decays over time because r is between 0 and 1. So there's an exponential decay. So this is your n and this is your r to the n. R to the n is the graph. What happens when n goes to infinity? Your Rn graph is approaching the asymptote and it approaches 0. That's important. Okay. As n approaches infinity here, when r is between 0 and 1, not including those values, then r to the n converges to 0. based on the graph. What happens when r is between -1 and 0, not including those values? So let's take r equals -1/2. So you have -1/2, then raise it to the power n. Now, because of that negative number, when you put odd exponents here, like 1 or 3 or 5, it's going to end up being negative, because -1/2 to the 1 is -1/2. -1/2 cubed is -1/2 times a -1/2 times a -1/2, which is -1/8. So all the odd exponents are going to make this graph oscillate in the negative region. But as you take even numbers, so -1/2 squared, that's +1/4. -1/2 to the power 4, that's going to give you +1/16. Those values are going to oscillate in the positive region. But as n goes to infinity, this graph's oscillation begins to stabilize. So this is n, that's r to the n. So notice I didn't draw a curve through it because we're only looking at natural numbers. That's why I haven't drawn a curve through it. Same thing for here. Although I drew a curve for it, essentially when it's natural numbers, you're just looking at points where there are natural numbers. And essentially it would only start from here, 1, 2, 3. We would really ignore that section. But the graph was just to help you visualize what happens of the behavior of the graph as n goes to infinity. The r to the n expression, that exponential term, converges to the asymptote 0. Same thing here. This will oscillate and eventually converge to 0 as well. So therefore, in the entire case, when r is between -1 and 1, the expression r to the n converges to 0 when r is between -1 and 1. So because it converges to 0, if we go look up here, we say that it converges to 0. That's where I get that 0 from there. Because essentially what we're doing is the limit as n approaches infinity. Now I'm introducing this new concept notation to you, which is going to be like, oh my gosh, where does that come from? Okay, all it just means is that imagine you are stretching all the way out to infinity for your n value. The way we write it is we say the limit as n approaches infinity. That fancy terminology just means that we can never actually get to infinity, right? You can't really get to infinity, but you can approach infinity, right? So that's why we use the word limit. And you'll actually see this limit, this word and this expression be more clearly defined when you do your differential calculus. But essentially the limit as n tends to infinity of this 1 minus r to the n term. I'm just going to leave a out here as the constant, right? Because it's not really being affected by n. Basically, this r to the n term converges to 0 as n approaches infinity. So this ends up being a times 1 minus 0. 1 minus 0 is just 1, so a times 1 is a. So that is why that only works when r is between -1 and 1. So what happens when r is outside that? So r greater than equals to 1 or r less than equals to -1. Well, when r is greater than equals to 1, you have this exponential growth curve. Again, with natural numbers, it would only really look like these dots here. But just to show you the behavior of the curve, as n goes to infinity, Rn diverges to positive infinity. That's not going to help us. We don't want things to diverge to positive infinity. The same thing for less than -1. What actually happens in this case is the most sporadic case. There's going to be these weird oscillations and it'll never converge to any set given number over time. So as n goes to infinity, this thing might keep growing and then suddenly come down again, then grow all the way up, or maybe it might come down over time. That's the sporadic nature of when r is less than -1. And that's why when we tell you to draw exponential graphs, that's why we tend to keep the bases between 0 and 1 or greater than 1. Because what happens when it's less than -1, it's no longer an exponential graph, it's this weird sporadic oscillation that begins to occur. So therefore, in either case here, there is just divergence. So that's the key word we use here. Your infinite series will diverge if your r is less than equals to -1 or if your r is greater than equals to 1. But if your r is between this interval, so if you had to visualize it on the number line here for r. So let's take 1 and -1 here. So if I put open dots on these two values and I put a line in between them, that is the interval of convergence. That's when your infinite series will converge. But let's put a different color here so we can emphasize it. if you now are on that side greater than or equals to 1, or if you equals to -1 and less than -1, so one of those two, then these intervals are your divergence criteria. So anywhere where your R is in the red zone, including those two endpoints, -1 and 1, then your infinite series will diverge. But if it's in between the blue interval, so not including the endpoints -1 and 1, but it's somewhere in between there, then your infinite series will converge to a finite value. Okay. So, what does it actually converge to? What is the whole point of this lesson? Using all that information we have, we can now write a formula for the exact value of a convergent infinite geometric series. That's the key word, because it converges towards a number. So if Tn is equal to a times r to the n minus 1, where n is a natural number, and that's the golden key, right? The crux, the holy grail, your r must be between -1 and 1, then the infinite series is said to converge to a finite number. And what does it actually converge to? Well, it basically converges to this. So the infinite sum is the limit as n goes to infinity, because you're adding up infinitely many terms of this expression here, but this is just your sum n formula, S sub n. So what happens? If you let n go to infinity, we saw that this Rn term converges to 0 as n goes to infinity, only when r is between -1 and 1. So if I plug that in, a times 1 minus 0 is just a, and that's all divided by 1 minus r. That is the formula. The infinite series formula, S infinity, is a over 1 minus r. So to work out what the finite value will be for an infinite geometric series if it meets the convergence criteria, it is simply the first term a divided by 1 minus the common ratio. And that is the infinite geometric series formula. I'll see you in the next one.